So welcome to this module number 3. We are going to discuss there is a heat treatment chapter. In that concept is age hardening or pitch of steels. So that topic we are going to discuss. First, before dealing with this age hardening or perception of hardening, that is precipitation of hardening, we understand what happened in certain metals and alloys. It shows the increase of in their hardness after allowing the sufficient time at room temperatures, so or after heating to a slightly higher temperatures. So this kind of hardening, what happens, we call it as age hardening. Okay, since this strength develops with the time or as the alloys ages, the age hardening is also known as precipitation hardening. That is, we simply call as pH of steel material. So because of this strengthening of an alloy results from precipitation of finely depressed second phase from the supersaturated solid solution with the passage of time. Okay, these alloys that are hardened by this process include aluminum and copper. Okay, so let us discuss about in detail about this age hardening process of steel. Okay, I will take up an example for copper, tin, or magnesium, aluminum, or sometimes steel and stainless steels. So now I'll take an example of age hardening of aluminum, the copper alloys. Okay, aluminum copper alloy. So let us discuss. There are different solution treatment. There are three steps for involving this age hardening process. First one is solution treatment and quenching and aging. So the solution treatment involves the heating of the alloys to certain temperatures that cause the alloying atoms, okay, to dissolve into solutions, so resulting in a homogeneous solid solution of single phase. This is going to be happen. Suppose if you take in case of aluminum and copper alloy, when the aluminum alloy is with 4% of carbon and it is 4% of copper, then it is heated to about 550 degrees centigrade. So once it is reached at 550 degrees centigrade and it held at that temperature for a while, and diffusion will occur and homogeneous solid solution of alpha rich in aluminum will be formed. So once it is formed, that will be considered for the point 1 on the phase diagram. So this is about the solution treatment. Second one is the quenching. The step is quenching. This is the second step of the precipitation hardening, and which is rapidly cools the homogeneous solid solution and and it is going to be freezes. So this is about the quenching. This atoms also it is under this solutions and this atoms allowing the elements do not have time to diffuse out the solution. That is, precipitation will not occur. So the solution becomes super saturated. Okay, and third one is third last step is aging. So aging is the process where the alloying elements diffuse out of the solution and into a cluster and distort the strength on the material. So this occurs over a prolonged time. It is not happen immediately. So after continuous uses of that material, this aging will be happen. So for example, in case of aluminum copper alloy take, this alloy is going to be heated around 165 degrees centigrade. That is in phase diagram point 3 is occur, okay, and it is held at this temperature for about 10 hours. So what happened, the fine precipitate of aluminum copper aluminum comes out at the alpha phase with the passage of time. Okay, so this resulting in this precipitation tends to very fine particles and depressed throughout the solid. Such a fine precipitate gives the much stronger and harder alloy. That is what that is aging is the factor. And suppose if you take for any partial phase diagram for any 96% of aluminum and 4% of copper, so we can view very clearly of their changes. So this precipitation can also occur at room temperature when the alloy is going to be cooled slowly. So but it increases if the solid is heated for some time, so the temperature being below the solvent temperature. So this hardness of this is going to be obtained from the precipitate when the heated for the some time is higher than the alloy where it is cooled slowly at a room temperature. So this is about the hardening, age hardening. So age hardening of steels is also, we must know that there are three types. One is austenitic oil, okay, and martensit oils and semi-austenite oils. So we must know that what are the pH of that. So for austenite oils, we'll discuss in detail. That is A286 grade. So what is the meaning of the A286 grade is, when the austenite precipitation is going to be hardened, the steel, then it remains there austenite structure after the annealing and hardening by aging process. So this annealing temperature of 1095 to 1120 degrees centigrade, the precipitation hardening phase is going to be consider remain in the solution. So for the remaining in the quenching process, when reheat about of 650 degrees centigrade to 760 degrees centigrade, the precipitation occurs and this increases the hardness and strength of the material. Well, come to this martensit alloy, it is 17.4 PS, that is 17% of chromium and 4% of nickel. That is going to be heated around 1042 1065 degrees centigrade. And semi-austenite alloy is 17.7 pH, means 17% of chromium and 7% nickel. It is also a very slow martensit is at very low temperature and the pH of steel is very soft enough to for cold working. So this is all about the different age hardening of steels. We'll see the process how it is going to be taken place, okay, in the video.
We most frequently receive concerns the chance to harden alloys using age hardening, a specific thermal treatment. This question is very common because every manufacturer knows how useful it is to have a hard, strong jewel, especially with thin or filigree parts that are so commonly used today. It is the kind of alloy used that defines whether an item can be age hardened or not. Sterling silver is well known to be age hardenable, whereas, for example, a traditional brass does not increase its hardness in this way. How does age hardening work? In a nutshell, the heat which is given to an item at a certain temperature and time induces a transformation in the alloy's microstructure, which makes the alloy harder and less prone to bending or scratching. The effect is measurable with a hardness meter, and it can be qualitatively experienced when trying to deform the piece. The working temperatures commonly used for silver and gold alloys are between 300 Celsius degrees and 450 Celsius degrees for a time of approximately 90 minutes, followed by an air or furnace cooling. A regular 750 gold yellow alloy is easily hardened at 300 Celsius degrees for 90 minutes. This is the so-called single-step age hardening, which works just fine on hardenable gold alloys. Silver alloys instead will benefit from a preliminary step named homogenization. This is a high-temperature annealing made between 700 and 740 Celsius degrees for 40 minutes, followed by an immediate water quench, allowing the microstructure to obtain the best condition for precipitation of copper particles in the silver matrix, later done at lower temperature. This is the two-step age hardening process. The actual age hardening process after homogenization is done at 300 Celsius for 60 minutes, followed by air quenching. So, what are the key points to a good age hardening process? The first is to have an alloy that has good properties to this concern. Some alloys simply won't harden, so it is of no use to try this treatment. The second is that the item should have completed all of its deformation and soldering steps before going into the hardening furnace. Annealing again or applying a soldering torch after the hardening would destroy the hardened microstructure. Most easily, you can get information on if one of our alloys is hardenable or not by just checking our technical data sheets, where for each title, the as-cast and after hardening hardnesses are reported. On technical sheets, you will also find the correct hardening furnace temperature. You can also get more detailed information and scientific background on age hardening.
I hope you understood the concept of age hardening by seeing this video. Thanks for watching this video, and other topics we'll discuss in the next video. Thank you.